Hello everyone and thank you for joining us. Today myself, Thibaut Gobet and our team will be presenting our project which is Password Strength Analyzer. This tool evaluates password weakness using real-world human behavior patterns instead of relying on outdated entropy metrics. Our team members are Alejandro Santana, Jaime Perez Selman, and Thibaut Gobet. I'll begin by explaining why passwords still fail today. For the motivation, why passwords still fail? Well, as you can see here, passwords remain the dominant authentication method. Even though we all know they are far from perfect, users naturally choose passwords they can remember, which usually means predictable patterns, short words, dates, names, or simple keyword layouts. Meanwhile, attackers no longer guess randomly. Modern tools like PassGun and Hashcat rule sets generate extremely realistic prediction based on leaked datasets and human behavior. And because of this, traditional entropy methods, the one that only look at character randomnesses, completely fail to capture real-world cracking difficulty. And that's the core motivation behind our project. We actually wanted a tool that evaluates passwords the way attackers actually approach them. In these slides, we are going to talk about the examples of real-world patterns. Large passwords leaks shows very consistent human habits. People love using dates like summer 2024 or 0101 2020. Names also show up consistently, Maria 1989, John 1234, and other P2 like fragments. Keyboard sequences like QWERTY and 1K, 1KAZ, 2WSX are extremely common because they are easy to type. And finally, users often repeat short chunks ABC, 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 or 2020, 20. These patterns heavily weaken passwords, and our analyzer is designed specifically to detect them. In the next slides, we're going to talk about the website interface. And this slide shows the public-facing website. The interface is built with JavaScript and runs entirely in the browser, meaning none of the passwords ever leave the user's device. It gives instant feedback on entropy, patterns, breach frequency, and name detection, all on one clean dashboard. With that, I'll now hand it over Alejandro, who will explain the system architecture and how the tool is implemented.
Thank you. Now I'll be talking about the system architecture overview of our project. So our system architecture is divided into two parts. The front end is the JavaScript analyzer, which hosts the website on GitHub pages in which the user can interact and input a password. From there, all of the information provided by the user is then forwarded to the backend, in which the Python Flask performs deeper analysis and runs the code locally. And the flow of information looks something like this diagram, where the user interacts with the website through the browser analyzer, and then the browser analyzer feeds all of that information to the Flask analyzer, which closely works with the different pattern modules used to detect and score the different characteristics of the password. And then once those scores are aggregated, it generates a report back to the user onto the front end. So our repository is organized with scalability and clarity in mind, so we kept it very orderly. So first, our key directories include the docs folder, which contains all of the live website and all client-side code. Our source analyze folder holds all of the Python logic of the different characteristic measurements of the password. Our source utilities folder contains all of the other helpful modules used for detection. The data directory stores all of the block lists and dictionaries and other names of files that we use to grab the top most common names as well as most common passwords. Our templates folder holds all of the Flask's HTML pages, And finally, the tests folder holds all of our unit test suite, which we use to modularly test each of the individual Python core logic modules. So now I will go over a front-end website demo. So first, we have an example of the live test feature on the website. So as soon as a user types in a password, the analyzer shows a strength summary, and it breaks it down into its core components. So the components are entropy, patterns, names, and frequency. So here on the visual bar chart, you can see suggestions to improve the password in real time. And the scoring is the website is very user friendly and gives immediate sense of what a password should be, either weak or strong based on the input. Now, the backend Flask interface, while the website demo uses smaller datasets, the Flask version uses the full block list and more advanced pattern matching. It includes multi-criteria analysis, color-coded feedback, visual charts, and tailored improvement suggestions. This makes the backend suitable for research, enterprise use, or other deeper analysis. And here we have the different detection modules that we implemented in our core logic. So the different characteristics we chose to measure were length and character diversity, or in other words, entropy, whether or not a password has been found on a breached password block list, i.e. the RockU list, dictionary words, repeated substrings or sequential keyboard patterns that are common in user-generated passwords, numerical sequences, PII-like structures such as passwords that contains names, years, or other personable information. And each module contributes a different score to provide a comprehensive weakness profile of the password. So now I will pass it on to Jaime, who will walk through the results and conduct a short live demo.
Thank you. Our results were very aligned with what the literature predicts. Weak passwords were immediately caught through block list detection, date recognition, or obvious patterns. Even passwords that looked strong to users, like long repeated sequences, were correctly flagged as weak. Most importantly, the JavaScript and Python analyzer gave consistent evaluation. These are actual outputs from the analyzer. The tool doesn't just give a score, it explains why a password is risky. For example, here we see warnings about breached frequency, dictionary structure, and keyword patterns. Users in testing found this is extremely helpful because it teaches them how to build strong passwords. When we compare human-generated passwords with random ones, the difference was clear. Human passwords almost always trigger multiple detectors, especially sequences and PII-like structures. Random passwords rarely trigger warnings, showing that the analyzer avoids false positives. We do have limitations. There is no deep learning model yet. PII detection is a heuristic only, and keyword path analysis is limited to simple linear sequences. Future improvements, including pass-GAN, style simulation, international dictionaries, advanced keyboard geometry, and API integration, so websites can adopt these analyzers during user registration. A demo of the Flask application that you can run locally on your computer. So this is it will show the features, the multi-criteria analysis like the length, the entropy, patterns, frequency, personal names. It gives you an explanation of the visual feedback, smart suggestions, and it's obviously this is all open source, free to use, modify, and contribute to your project. So let's start testing a quick example here. We're gonna type Alex, and we're gonna analyze the password. Here are the result. This password appears in common password list and may have been compromised. This is the overall score. These are the suggestions, like make it longer, at least 12 characters, more variety, and avoid common passwords. Now let's go to a random generated password. Suggestion password here. This obviously will give you overall strength of 100%. Here we got the entropy, the frequency, lengths, names, and patterns. If we delete this, this is the password that we use. This is our JavaScript running on live from the GitHub pages in our repository. So we have a different design, more user-friendly for anyone that wants to use our projects and test it and contribute to them. This is we explain what we check here: the entropy, the patterns, the brief frequency, the names, and then we got this is the section that what it test covers, kind of same explanation how it works. Scoring, we weigh the aggregation of normalized subscores, the data, how we check the data, the suggestions, the privacy regarding this, and then it gives you an explanation on how to deploy and run the full analyzer on your local computer. You can clone the Git repository, install the requirements, run your Flask app locally, and that's what it will be generated on your end. So here we're gonna put multiple times the number 9. Here it will trigger the patterns and the sequencing. We got no entropy patterns. You got like an 80%. So this is a moderate password. As we say, this is just for the sake of the test. And then we're gonna run now a recently generated password that we used before. This is a random generated. I give it 100% score. To conclude, password fails because humans are predictable. Entropy alone cannot capture that. Our analyzer focuses on behavioral patterns and realistic attacker logic, offering clear, actionable guidance. The dual architecture approach makes it both accessible and powerful, and we believe this research can contribute to improving password hygiene.